What's up, team? This is Ro, your best friend at JMSB. So here I was asked a question for COMM 215, Introduction to Business Statistics. Example 8, let's have a look. Here it says, a job training program offers training in advanced computer programming. It is suspected that the probability that an individual will be able to find a programming job within 6 months after the completion of the program depends on previous related work experience. A random sample of 80 individuals trained in the program yields the following frequency table. So we see that the number of years of experience could be 0, 1, or more than 1, and then we have the number of individuals with either 0, 1, or more than 1 years of experience, so 52, 16, and 12. It then tells us that of the 52, 16, and 12 individuals in the 3 experience categories listed in the table, respectively, 20, 8, and 10 were able to find a programming job within 6 months. So in each category, here we're offered how many individuals were able to find a job within 6 months of applying for it. So let's have a look at required A. In required A, it says, at a 5% level of significance, is there any evidence to support the hypotheses that the probability of finding a job within 6 months depends on prior related work experience? So here what we have is a very typical chi-square test for independence. We should be able to detect that it's going to be a chi-square test simply because they're asking if the 2 variables are related or not, and the data set has sort of been offered in a contingency table or within categories. So these are sort of hints that it's going to be a chi-square test. Now regardless of that, regardless of which hypothesis test it is that you're doing, the steps that you have to follow are really the same. The very first step of any hypothesis test is to express the null and the alternate hypotheses. In the case of a chi-square test for independence, in the null hypotheses we always argue that the 2 variables are independent, and in the alternate hypotheses we're testing if they are dependent. So we're testing if they are related or not. And so you'd want to express the hypotheses exactly like that. In HO you could say things like probability of finding a job within 6 months and prior related work experience are independent, and in HA you're going to want to test whether the probability of finding a job within 6 months and prior related work experience are not independent. The next step of any hypothesis test is to calculate a test statistic. Now when it comes to a chi-square test for independence, this is perhaps the most tedious step, and it's simply because it involves a bunch of repetitive calculations. So in the second step, we're going to try to calculate the value of our test stat. In order to do that, the very first thing we should do is set up a table where we keep track of the observed values and the expected values. So in this particular example, we were offered a table in the problem where they told us the years of work experience and the totals for each category. And then lower down, it explained to you how many people in each category have found a job within 6 months. And so, since we know how many people have found a job, we can calculate how many people did not find a job. So for example, in the first category, out of the 52 people, we were told that 20 found a job, and so we can calculate that 32 did not find a job. So at first, we're simply going to repeat that for each category and determine the observed counts for each cell. Once we've done that, the next step is to calculate the expected counts for each cell. The expected counts are the ones that I've sort of written in blue here, and the way that you get the expected value for a cell is by multiplying the total of the row by the total of the column and then dividing by the sample size. So for example, the way I calculated this 24.7 was by multiplying the total of that row, which is 52, by the total of that column, which is 38, and then dividing by the sample size, which is 80. So the idea is to repeat that 6 times, and you want to calculate the expected value for every single cell. So to make sure that you guys got that, we can try out another random cell to make you understand how I found this 27.3. I would multiply the total of the row, 52, by the total of the column, 42, and then divide by the sample size, 80. So far this is a calculation that is pretty straightforward, but it does have to be repeated 6 times just to get the expected counts. Now once you've found the expected counts for each cell, the idea is to apply the equation for the observed value for chi-square, or the equation for your test stat. Your test stat is simply the observed count minus the expected count squared divided by the expected count. So we want to repeat this calculation for every single cell, and we want to add up totals. The result will tell us our chi-square observed. So in this expression, I remind you once again, Fij are the observed frequencies. So these are the 20, the 8, the 10, the 32, 8, and 2. And Eij are the expected counts, the ones that I've written here in blue. And so if you work that out, you're going to essentially be able to repeat the calculation 6 times. The reason why there's a double summation is simply because you want to repeat this calculation for every column and every row, and you want to be adding up the terms. So if we work that out, we should end up with an answer of 7.922 as our observed value or our test statistic. Now once you've found the test stat, the next step is to either find a critical value or a p-value. Try to remember that this step does not require the use of a calculator. All you're really going to be doing is either using alpha and the chi-square table to get a critical value, or you'll be using your answer from the prior step to obtain a p-value. So what we're going to definitely need is our chi-square table. Suppose I want to get a critical value. The way that I do that is very straightforward. In the very first column of my table, I go to the appropriate degrees of freedom. The appropriate degrees of freedom is simply the number of rows in our table minus 1 multiplied by the number of columns minus 1. So since we had a table that was a 3 by 2 table, the degrees of freedom is simply 3 minus 1 multiplied by 2 minus 1, and so you're going to have 2 degrees of freedom. In the very first row of our table, we're going to go look for alpha. The value of alpha is usually offered in the problem. If it's not, we assume it to be 5%. In this example, alpha was in fact 5%. And now if we connect these two, then from inside the table, we can go ahead and get our critical value. So the critical value for chi-square is going to be 5.991. So when we're looking for our chi-square critical, we have alpha and 2 degrees of freedom. And once again, I remind you that the way we got these 2 degrees of freedom is simply because it's the number of rows minus 1 multiplied by the number of columns minus 1. The alternative is to use the p-value approach. Under the p-value approach, we begin by going to the appropriate degrees of freedom. So we're going to go down to 2 degrees of freedom. We're essentially going to stay on this row and we're going to scan this row until we find a value that is bigger than our test stat. So our test stat is 7.922, and so the value that's just bigger than our test stat happens to be 9.21. So we essentially stay on 2 degrees of freedom, we scan that row until we find a value bigger than our test stat. Once we've done that, we're simply going to go up to the very first row of the table and grab the p-value from the first row of the table. So we could argue that the p-value would have to be between 0.025 and 0.01. So it's bigger than 0.01, but smaller than 0.025. So if I had to express the p-value, I'd simply argue that it's between 0.01 and 0.025. So now that we've gotten the critical value and the p-value, the final step of any hypothesis test is really just to make the decision. And now when we want to make the decision, we can either use the p-value approach. Under the p-value approach, we're going to compare the p-value to alpha, or we could use the classical approach where we compare the critical value to our test stat. So we're able to say things like, since the p-value is smaller than alpha, or because the test stat is larger than the critical value, we're going to reject HO at a 5% level of significance. Whenever you make your conclusion, it's a pretty chill idea to repeat the level of significance. Furthermore, understand that when you're rejecting HO, you are arguing that the two variables are not statistically independent, and so they are related. And And for that reason, you could say things like there's sufficient evidence to support the claim that prior years of related work experience and the probability of finding a job within 6 months are related. To help you visualize this concept, imagine if I were to draw out the chi-square distribution. Realize that the critical value that we found is found using alpha, and what it does is that it separates the HO region from the HA region. So it separates the acceptance and the rejection region. And now one way to make a decision is to compare this critical value to the observed test stat. Our observed test stat was 7.922, and so clearly we can see that it falls in the rejection zone, and so that's one reason why we should be rejecting HO in favor of HA. The alternative is to compare alpha to the p-value. Alpha is this area that's found in the tail in our rejection zone. The p-value is the area that is found on the right of our test stat. It should be pretty obvious to us that the p-value, the area on the right of 7.922, is much smaller than alpha, which is 0.05. And so whenever the p-value is smaller than alpha, now again we are going to be rejecting HO. So I hope this explanation helps. This is a very typical exam-like question, so I hope that you guys keep practicing more questions if you don't quite get it yet. In the meantime, if you found that this video was helpful, make sure you tag your friends in it. If you know people that are taking the same class as you and you want to help them out, tell them about Ask Ro. I hope you guys keep well. Good luck for game day. Ro out.